So without further ado, I'm going to introduce our speaker. He got his bachelor's in the University of Texas at Houston. He got his master's over at USC. Go Trojans. He did a brief stint in LA, working in geotech before moving on to the California Geological Survey, where he's part of the landslide mapping program. And he's going to talk to us this evening about shallow landslide and debris flow activity recently in San Diego. So Paul Burgess, take it away.
Okay, well, thanks a lot, Luke, and everybody can hear me okay, I take it. Let's see here, I'll go ahead and share my screen, and when I do that, just I guess Luke or anybody really give me an audible if you can see the slides here. Is that good? Yeah, thumbs up. Okay, great. Well, let's see here. Okay, so that's good. We'll get to that next slide in a second here. Luke, I just want to say thank you for reaching out. I know that we all live in really strange times, but we're getting through them. And between Luke and Lynn, and then also Diane Murbach, who heard me give an earlier version of this talk. Diane, you'll probably see many, if not all, of the same slides because the talk hasn't changed too much. But at some point, Diane saw that talk and she got in touch with Luke. And anyway, he recommended, or he asked if I was available. And like we know, it's, unless you've really got something special going on these days, where most of us are pretty available and eager to, see one another's face and just kind of explore the geological world outside of our own wheelhouse. So for me, this is also special because it's good to be back in Southern California. I just moved back to Los Angeles actually about 4 months ago, October of last year. And before that, I was based up in Sacramento, which is where I worked with many of the people that you see on the screen here, and I'll introduce in a second. And that's where I started off with my time at the CGS, but I was able to transfer to the office in Los Angeles, and it's good to be back. The first time that I came to a South Coast Geological Society meeting was actually 7 years ago. It was in 2014. And at the time, I was relatively new on the scene, looking for opportunities in the geotechnical world. And it's a very special honor to go to a meeting, and several more since that time over the years, and now to be here to be one of the people that gets to, share my time and some geological insights with all of you and to present. So it's pretty cool. I also want to give just a shout out to some of the people on my call. You guys were able to meet my mom, who's visiting all the way from Texas, because like all the rest of us, she doesn't have too many things going on tonight. So she's here to see what I've been up to. Ron Mendeville is a former colleague of mine. I worked with Ron when I worked in Los Angeles at Pfeffer Geological Consulting. And also shout out to Pfeffer Geo, which is a boutique firm in Los Angeles that does a lot of work. They kind of have their sort of interests in all sorts of different projects and scopes of work around the LA area. And due to the experience that I gained working at Pfeffer, that's what gave me the experience that I was able to carry forward and take with me to the CGS. So with that round of introductions out of the way, I'll highlight the people that I've worked with on this project here. Alex Moreland is a coworker of mine at the CGS. He's based in Sacramento. He got his PhD out of Davis. He's a relatively new hire, came on board last summer. Stephanie Lukashov is also in Sacramento. She's with the Forest and Watershed Geology group of the CGS. Chris Henningfeld is a very dynamic student assistant that we have that has done a lot of powerful work in tracking down recent landslide data that I'll explore a little bit during this talk. Nina Oakley works at the Center for Western Weather and Water Extremes, which is sponsored through Scripps at UC San Diego. She and her partner, Ben Hatchett, were responsible for some incredible figures and modeling that you'll see shortly regarding this atmospheric system that created all this rainfall last year in San Diego. And then Carlos Gutierrez and Jeremy Lancaster are also at the CGS. Carlos is a GIS mapping guru there and had helped me out with many of the figures that you'll see here today. And Jeremy is he's the supervisor of the Regional Geologic and Landslide Mapping Program there.
Hey Google, stop.
So let's see here. And then a few other acknowledgements go to the tennis club in Encinitas, the San Dieguito Tennis Club, where we received some really just excellent photographs and drone footage that we used to do our topographic modeling for the study. Tony Villasenor is one of the people that lives across from the tennis club and was able to capture some of the very early footage of the debris flow that I'll talk about. Ben, I mentioned, he's at the Desert Research Institute. Douglas Alden is at Scripps, took a lot of photos, and then Janice Hernandez and Jose Hernandez, no relation to one another, work at the SCGS office here in LA. And then Ryan Smith is a good friend of mine who was able to do some site reconnaissance to help me take a look at the site before I was able to travel down there. So with all that out of the way, this is what I wanted to share with everybody. We made it beyond 2020. So you can see here that in this particular image, the world is on fire. There's a senior center that is facing imminent destruction. And on top of that, we've also got, COVID-19 protocol being advertised, about to get flamed up there. And last year was a rough year. This year, we're on to brighter pastures, as much as we can all hope and actively work hard for. So let's keep charging. For today and what I'll talk about, we're going to go over these items. And as Luke mentioned, if you have questions, just type them into the chat box, and we'll make sure to cover them at the end of the talk for you. So we're going to talk about the weather leading up to the spate of landslide activity, how we collected the reported landslide data from crowdsourced data, which motivated my field trip from Sacramento down to San Diego at the time. We're going to look at the timing of the landslide activity with respect to triggering thresholds in terms of precipitation, looking at some field mapping techniques, and then talking about structure from motion modeling, which is what we use to build a topographic difference model. And the motivation for this is right here. You can see that you've got a pretty sizable debris flow that is originating from that escarpment in the background of the photograph, and it's ripping into the center of the photo and into the foreground. And you can see that these tennis courts luckily served with their fences as sort of like an ad hoc debris barrier. And if they hadn't, then this drainage, which is at the the top of a small but nevertheless map scale alluvial fan, would have done its alluvial fan thing and allowed all of that sediment and debris-laden flow to deposit itself over a lot of other infrastructure and critical businesses at the bottom of the hill. So we'll get into that in pretty nice detail here shortly. This is what was responsible for that particular devastation. And these next series of figures that you'll see come from a paper that I was part of to contribute some information in terms of the landslide data that we collected to Nina Oakley and several of her colleagues at Scripps at the Center for Western Weather and Water Extremes. And as you can see in the slide, the title of the talk here, or the paper that she put out, it's a small but very informative one. If you all are not familiar with atmospheric river dynamics, or even just major precipitation events that are published through the CW3E, this is a really good paper to take a look at, because for last year, it represented one of the most significant amounts of rainfall that the state of California saw, especially the southern half of the state. So it's pretty cool that I get to present this topic and hear your input on it as fellow local Southern Californians, although you all have been around way longer than I have down here. And you can see that the area that's largely impacted in the storm as we go forward is from LA, it's even the Southern Sierra south into the entire southern part of California. So it was April 4th through 11th that we had this really damaging rain, and it was produced by a cutoff low, which is what it sounds like. It's just a low pressure system that is cut off from the prevailing jet stream. And as a result, it can do a lot of damage because it kind of moves when it really wants to move, unless something else moves it. And once it's cut off, it's not being entrained in the regular flow of weather. And that creates a lot of problems that don't happen too often, but when they do, they deserve us taking, or scientists taking a deeper look at them to figure out what can be done to understand them. So here you can see, this is another figure from Munis paper, and you can see that for the period of April of last year, you can see the percent of normal, or another way to think about that is the percent of average precipitation that that part of California here, Southern California, received. And I apologize if this is not, if some of you may be colorblind in any way. There's a lot of very vibrant colors on here, but hopefully most of you can see it. The very top part of the scale here, the 800, is the exact same bright fuchsia purple color that you see here that's impacting most of Southern California, even inland Southern California, where there's a lot of desert. And so that just shows you how anomalous this storm system was, as it produced up to 800% of an average amount of rainfall expected for that time of year. So it's intense. Moving forward, we'll take a look here at an animation that will show you figure 3 from that paper, which is showing integrated water vapor transport, which is just showing you an atmospheric, just a quantity of water, like a column of water moving through the atmosphere. And you'll see this intensity measured in, this darkening green color scale, light green to very dark hunter green here, that shows you the intensity of this water and this precipitation as it just stalled out over Southern California. And what you can look at here in the, let's see here, there we go. It glitched out for a second. Let's see if it, yeah, now you can see it. So what you can look at here in the top right of this graph is it'll show you the time and the date, this universal time, and it'll show you, basically just the storm system as it moved through that week. The 11th of April was Friday, so you can wind the clock back and get back, to the start of the week, and you can see this. Actually, the 10th of April. Sorry, it was Friday, but so the 5th would have been Monday or Sunday, actually. But what you can notice here is that as we move through this this graph, just showing you where these sort of isobars are and how they're just sort of steadily just creeping along the southern coast of California and then just hanging around on the very southern part of it here. It's just so much water that is getting scooped up, being pulled up out of the ocean. It's being entrained in the atmosphere that's locally being cut off, and that's just being dumped on the landscape. And people saw a lot of rain, like I mentioned, in the desert areas of Southern California, and even in parts of Western Arizona with this system. So there's a lot of water, and it took quite a bit of time for it to move on past California. You can see here too that here we are now. It's April the 10th. Now we're into April the 11th, Saturday, early AM hours, and finally this this system is moving beyond. So for a week, people that were living in that part of California, and I assume many folks that are on this call, directly felt that rain last year. I was in Sacramento, so I didn't feel it. It was a little bit rainy up there, but I know that Southern California got hammered. So some of you might even have, might even recall hearing some of your neighbors or even maybe yourselves thinking, if you've been around long enough, that possibly could have been the most amount of rain that you'd seen in your lifetime for that part of California. And I think that that's an accurate statement, because based on estimates of the data that we've seen and what we've collected for this part of California, that we're looking, that this was a storm event that has an upwards of possibly way beyond a 200, possibly even upwards of a 500-year recurrence interval. So it's definitely extreme. And zooming in on the area that we want to get interested in and what we want to look at around here, you can see that there's a series of colored circles that are inside this black square on the left-hand side, which is showing you a radar image, radar reflectivity. This is on April 10th. So just before midnight on Friday. And you can also see that there's a series of black triangles. These black triangles are also landslides that were reported as of the next morning on Saturday, April 11th. What you can see is that it's really bright. And this is just, one moment in time. This area was, sustained, it faced sustained rainfall in all these stations. As you'll see next on the next slide, which is just showing you here a hydrograph, and this is showing you this data as we go from Monday, the 6th, through the end of the week, the 10th. You can see it steadily ramping up it's cumulative, obviously, but you can see that there's a really aggressive rise in the rate of rainfall that's being recorded in these different gauges that are all over San Diego County, especially northern San Diego County. And you can see these incredibly sharp inflections that happen here at the end of the day on the 10th as we move into the 11th. And that shows you the intense period of rainfall that happened on Friday afternoon, the last burst, which was actually responsible for the debris flow that we'll talk about here tonight. So this is some data that is important to include because what it does is it shows you the efforts that we've made. This was with some of the help that I received from Stephanie at the SCGS, who has been doing a lot of work processing rainfall data for different forest and watershed projects. And what you can see here is that we're looking at, the known history at the Encinitas gauge, which goes back to the, the early 1960s, 1963. And, for every water year, what we've done is we've included a bar to represent that water year of the, basically the maximum storm total rainfall per water year. So per storm, what was recorded, what the maximum was, just to contextualize how much rain fell this last year. So it's, easily an order, maybe 1.5 times, easily 2 times order of magnitude difference from what the running average is, maybe even 3. And these blue dots and these white hollow dots are showing you some different pieces of data. You're looking at the 1 hour precipitation intensity for a storm event. So for each bar, what that actual storm intensity was for an hour. And then also in comparison, what the maximum 1 hour precipitation intensity was for the overall water year. So you're going to have a little bit of spread because sometimes you may have storms that are not so intense, but they may have very intense rainfall. And so we want to contextualize the way that the rainfall data was being recorded. And you'll notice too that there are gaps in the record, and those gaps are because this gauge has not been here as long as another regional weather station, which is down at San Diego Airport, or formerly Lindbergh Field. And that has a very comprehensive record at Lindbergh Field. So we wanted to make sure that the regional precipitation trend that we were seeing in Encinitas that we're going to report in order to compare it to this last year is somewhat on par with what was regionally being recorded in the greater area and with a more robust rainfall collecting apparatus, which is what we had at Lindbergh. So the cutoff is that if not more than 50% of the water that fell at Lindbergh was also recorded at Encinitas, we left it off the graph because we wanted to be conservative and not overinflate or, in a sense, underreport the actual measure of worthwhile precipitation to report for Encinitas or for the northern San Diego area. So here you can look at a series of 4 graphs. I'm going to zoom in on all of these hydrographs and walk through them. But just showing you the approach that we took to look at this rainfall and contextualize it. We looked at the 2020 water year. We looked at 3 months out. We looked at a month out, and we looked at a week out from the actual event that was being that we were studying here. So for the year, you can see here that this is a cumulative hydrograph, and it's showing you what the precipitation intensity is, these blue dots for various storms, how that's tracking throughout the year, throughout the water year, from October 1st through, at that time, April. And what you can see here is that essentially we've got this massive amount of, stormfall, rainfall intensity here that happens, easily, again, almost another order of magnitude higher than the amounts that you're seeing previously up to that point in the water year. And that's important because, with triggering thresholds for landslides with rainfall, people are very interested from the USGS on down to, weather services, and anybody studying this topic, you want to look at how much antecedent rainfall has fallen, because it's kind of a competing contest between the rainfall and, of course, the strata or the rock or the soil, or many other factors, how they all work together to, produce a lack of cohesion and generate a landslide. But knowing exactly how much rain has fallen and then looking at the geology and whether it can take that hit, can drain that water, or whether it can't, or what it does with it, that's important. And so that's why we're contextualizing from the water year out through, 3 months out now, taking a look here at these, massive steps in the hydrograph starting in March, and then really ramping up by, more than twice in the month of April alone, to take a look at how the soil is dealing with this rainfall as it's getting prepared to unleash itself in the form of a debris flow or a landslide. So you can see here that there's periods of incredible wetness every time that there's a vertical step in the hydrograph or a sustained rise in the hydrograph. And you can see that you've got just enough periods of wet, but then we have this 15-day dry period, which to me is one of the reasons why we didn't have more landslides that were more potentially either deep-seated or at least more widespread across the region, because there was enough time for the ground to dry out just a bit. And for 7 days out, you can see here, this is a dramatic amount of rainfall. And so, if we receive 524 millimeters over the year, we've received almost half of that amount, 188 millimeters of rain in just this 1 week alone. So understanding the meteorology and the rainfall is obviously crucial to any landslide study involving precipitation as a trigger. So what happened and how did we get here? It's interesting because many of us, as we've seen, we live in a world that's very dynamically influenced by the data or whatever you want to call it, whatever is being put on the soundboard out there in the world of social media. And one of the great things about Twitter is that when you're working with people who are reputable contacts and people that you trust, and then they have something that they note and they highlight and it pops up into your field of view, you can get a time and a date stamp. And if you're lucky, maybe even some people that are, the debris flow or the phenomena being reported on. And so that way you can start to reach out and contact people and correspond with, local agencies, local citizens, and then begin a search for photographic evidence and do what you can to try and figure out what actually happened. And we all know, whether it's, Brian Olson at the start of this was talking in the introduction, like much of his job this day, and the same for all the rest of us, is looking at a lot of satellite photography and, making, calls on, what you're looking at. And we all do that. And we're lucky, as geologists to, have exposure and to take opportunities to continue to train, because photographs, satellite data, drone produced photography, photogrammetry in some of the older school times of looking at maps or detecting geomorphic surface changes. It's all crucial. And so the more access you have to that data, the better you can decide, did a landslide or did multiple landslides happen? And then once you see more than one, and once you see them happen across a wide swath of an area, that it actually matters to take a look at what went on. So this is the database that we've been putting together at the SCGS over the last year and a little bit. You can see, if you look at this map, that we've got a series of smaller triangles that are along the coast. These were slides that we had spotted or that were reported through crowdsourced data through people in the community or fellow geoscientists, and even people who might just be driving down the road and see a landslide and take a picture. And actually, while I'm on that subject, I would encourage all of you, we're about to get, according to the National Weather Service, another nice dose of rain potentially over the next 7 to 10 days. And, if you're out there in the world and you're driving along and you see a landslide, the way that landslide studies are made better is we have to have the evidence of the actual volume of the landslide. If we take a look at a spot where a landslide happened, it helps because you can say, oh yeah, well, that slope was steep and it was raining and etc. But it's not until you can actually, equate the volume of material that slumped off of a slope with the actual moment in time that it happened that you can really pinpoint those triggering thresholds, because rainfall data is very, hard to come by to begin with. And because you often get it depending upon how, well engineered the collection devices, or if the telemetry is off, you may not get data sent through when you need it. And so to make up for all of those gaps in traditional ways of reporting rainfall, another way to do it is to take a look at the actual photographs that are coming in from the community that people are sending and saying, hey, I saw a landslide at this time and date, here's a photograph of it. And that's great. So if you see landslides, just from now forward, do me a favor. And if you have time and you can remember, please send them to me and I'll feature you. I'll make you famous on our landslide database here, which is growing every day. So we can talk more about that later, and feel free to ask me questions about that. But it's a great educational tool that we're trying to build, and which will eventually become a very robust repository for doing landslide science. So what you can see here is all of these news slides. These are the news slides that were either reported from people in the field or slides that I observed when I drove down to Encinitas to take a look at the field area. And then there are potentially even more to come after we get our hands on some more landslide data, some satellite data that we've asked the USGS to try and collect for us through digital globe worldview imagery. We'll talk about that a little bit more. This just shows a few of the driving tracks just in orange here. You know, the thing is that I would have loved to have been down there even longer. But, you know, keep in mind, this is the end of April. We don't even know what in the heck is happening with this pandemic that just seems to be just ramping up and up and up. And like every day is a new threshold of just terror. And in many ways, for many people, unfortunately, it still is. And so at that point in time, though, with just so little that was known about it, the key objective seemed to be, you know, get down there, be safe, don't get sick, collect data, you know, talk to people, take a lot of photos, and then, you know, come back and then let's process it. Let's think about it. So when I say crowdsourced data, I'm talking about everything as basic as looking at news reports. Some of you might even remember seeing some of this footage, you know, from that week in April. And, you know, for many people that aren't, you know, sort of familiar with the importance of categorizing landslides, you might think, okay, well, you know, I know, for example, Ron on this call here and so many others of you, you know, working for geoengineering firms and whatnot, you know, it's a topic of office conversation when it's a rainy day and you're on your way to work and there's all hell's broken loose up some, you know, any number of canyons around LA or elsewhere in Southern California. And everybody's, you know, giddily looking at the television screen with this, you know, looped footage of just destruction. This is small scale compared to what many of us see in our typical, you know, rainy times in winter in Southern California or across the state. But there's a few things that pop out here that make it important for motivating, you know, what's going on in this area with all these storms. One, this is obviously a nursing home. You can see that from the screen here. But two, we've got a pandemic. So, you know, you've got 24+ people, senior citizens, very elderly folks that are having a hard time dealing with life for that phase in their life at that time anyway, to begin with. And now they have to be evacuated in, you know, just very quickly changing circumstances. This particular slide, there's not too much more based on what you can see here on the screen, but I show it because it just represents one slide that is, you know, part of a series that has, you know, different components to it in terms of scale. And when you combine them all together, it warrants, you know, it justifies, you know, me as a scientist working for the SCGS to, you know, to make use of, you know, state funds and resources and drive and spend time and take a look to collect the data that's important to, you know, collect because it's perishable. So this right here is the video that was originally featured on Francis Renger's. He's a geomorphologist, works with post-fire processes at the USGS. This was featured on his Twitter profile. And so when I saw this and when I saw that it was in San Diego and then saw all the other data that came with it, you can see that the motivation is, you know, is pretty easily there for understanding what's going on. Now, Francis at the time brought this to my attention because he was not sure whether this area had burned at all upstream of this debris flow, because debris flows following fires, we're all familiar that that's you know, that's like bread and butter. They just go together. And so it was unclear what triggered this debris flow, and that's what launched our investigation. You know, as the CGS does, is to try and, you know, work on identifying and mitigating hazards, whether seismic or any geologic nature, as they impact Californians and California businesses statewide. So I mentioned at the start of the talk, Tony Villasenor, the gentleman that lived across from the tennis club. This is the view from his balcony. So he's the one that shot that video. So, you know, the credit goes to him for starting this project. And the other thing that Tony did that you'll see in a little bit is that he got one of his friends to come out and fly a DJI drone over the debris flow. And it's incredibly lucky that he did, because that drone footage is where we got our structure from motion topographic modeling data. This is in Solana Beach. If there's anybody on this call from Solana Beach, you know that large neighborhood areas in Solana Beach got hammered by this rainfall. Here you can see that, you know, this is how it is. You know, anybody who's read, you know, The Control of Nature by John McPhee, or just spent a lifetime of work. You all have decades beyond my experience in this field and around this part of California, but it's a great example of nature being fickle. You've got this very well-designed, drainage here. It's almost like some landscape art in a way with these blocks to, kind of keep the water from getting too channelized. And yet, nevertheless, the water just wants to come out just exactly adjacent to it and create this slump. So again, this is just one isolated event, but what made this storm exceptional is the volume of slides. There were over 40, and like I said, if we pick up more in the data that we'll process later, there could be more than that, which would make the event more significant than it already is. There's another view of that particular slide in Solana Beach. That's April 9th, so that's midday. So that's before the real brunt of the rainfall kicked up. This is another view, a typical sort of graded hillside. This is here in the city of Encinitas. This is right at, I would call it, the top of Encinitas. I'm blanking right now on the particular street that this is on, but geomorphically, this is literally at the top of Encinitas. There's a bluff, there's a high ground area, and this is a north-south road. And so you can see the sun is low in the sky. The view on the photograph to the right is looking off to the northwest. The view on the photo to the left is looking to the north. But what you're looking at here, and many of you are, again, you're experts because this is your backyard. So you can see here that you've got some relatively flat-lying Torrey sandstone. It's essentially free draining in terms of the geotechnical, what's the word here I'm looking for? A geotechnical property, when you're looking at, water draining through the substrate, when you're trying to, engineer how to deal with drainage on a project site. So, thank goodness that it is, because that helped a lot of the water actually, evacuate through the rock vertically instead of dislodging more of that actual rock into deeper seated slumps. So what we're looking at is a lot of typical, very shallow soil failures. And you can see here that this colluvium, some of this is probably just arguably not really well engineered fill that was placed on the surface. It's cut back at about a 2-to-1 angle. So, to keep people satisfied in terms of, municipalities and city codes and county codes, I imagine it must be similar in San Diego as it is in LA. 2-to-1 is fairly acceptable, but with this amount of rain, even that is no match for the soil to fail. And this is another example of a slope that was even very well planted in Rancho Peñasquitos. So this is inland quite a bit. But again, it didn't matter, because due to the volume of the rain, and also thanks to COVID-19 for what it's worth, on an hour of day at 9 a.m. in the morning that typically would have been rush hour, nobody was driving on that street. So nobody was affected by that slump. But you can see here that, again, you've got a large amount of surface soil vegetation just wiped out. And that's not even your typical, what I would arguably call, your relatively worthless ice plant that looks good, but it doesn't really do anything to keep the soil held together. This is actual, decent, well-rooted vegetation that just got ripped out. So the pervasive set of slides that happened all over the area led us to take a look back at some of the existing geologic data for the area, which is, where we all start, or where we would like to, if we can have access to it. And sometimes it's hard to find it, on the internet these days. It's, it's a little bit easier sometimes, or depending upon who you ask. But this particular map that you're looking at here was produced in 1986 by an old SCGS geologist, and it's 3 plates that are the same area. But what they're showing you is the relative landslide susceptibility in 1, landslides and steep slopes in frame 2, and then a geologic map in frame 3. So one observation here is that the existing data, like a lot of geologic maps, it can be old, but it can be accurate. And so that's important to pay attention to. It doesn't matter if you have some newfangled way of making a map, you'll always go back to the original data to get to the source. And so the red star is where the debris flow happened at the tennis club. Many of you are probably familiar with this area, I would assume, if you're in that part of San Diego, and you probably, you might have even driven by it the day after it happened. I'm not sure, but you would have seen a lot of mud and debris on the road, this north-south catchment here. And you can see that we've got numbers. We've got a 2 over here. We've got 3 in the middle by the star. We've got other areas that are hashed, etc. And what we're going to look at here in the description is that, this explanation of this relative susceptibility is that this is a generally susceptible area. So that seems to apply to, much of coastal California. But when it's modified by processes or activities of man, because they're close to their stability limits, they can potentially be at risk of suffering from debris avalanches, or also called debris flows, or soil slips. And then that can originate in these, steeper areas and then flow downhill, which is common sense, but it is important to point out on a map for anybody that, may not, go to that logical point first when they're trying to process how to, look at this data. And then another note that Sang made in this map is that, it's possible that the modifications to the landscape by the activities of man may significantly alter the relative stability of the slope. So he points that out and says, hey, this might change in the future, so be alert. Now, what's curious is that in terms of this whole area where all these slides happened, the debris flow is, well, aside from all the slides that happened in Solana Beach, there's a cluster kind of in the lower center part of your screen. That's one neighborhood in Solana Beach that really got hammered. Aside from that area, the debris flow is an example of just an egregious lack of planning, and in some cases, more than arguably, criminal, lack of planning and dangerous, dangerous landscaping that conspired with the existing geology to just, really wreak havoc on the area. And the reason why that not more happened in this area is that because, again, I think the threshold is that with the rainfall that fell, there was enough time for the soil to dry out, coupled with the fact that most of the underlying sandstone was actually able to help the water drain out of it, that saved the area from facing more destruction than it already did. Now, for all of the locals in the crowd, you look at a map like this, you've probably seen it a lot before. This is from a SCGS map. So this is from 2007, part of the Oceanside 30 by 60 quad. I just put this up here because invariably, folks will, be curious about some of the nuanced details of the actual stratigraphy and the geology. But in general, I don't like to have so many words on a slide because it probably induces a headache. So I apologize. But on the right-hand side of the image, I'd just like you to take a look at and kind of train your eyes in the center of the image. And what you'll notice is that right where that QVOP12 is, we've got a cap of some Pleistocene gravels and conglomerates there. And that's overlying, again, this Torrey sandstone. You can look, and I'll make it easier for you to see in a minute, but there, of course, is, infrastructure. You can see some roads. You can see those roads and those, purple lines sort of arcing around following the topography. And you're looking at the community that we're going to get into here in Solana Beach that was impacted by these slides. To contextualize what happened in Solana Beach, we did a check with the help of Janice and Jose at the Los Angeles SCGS office to find air photos in the data repository. And it's tantalizing what we found, because we got photos where you're looking at the red dot as the centroids of the photos that were taken in 1970. And that's what the air photo availability was at that time. So almost the area that the debris flow happened in, but we did get some really nice views of Solana Beach in the early days of development, and you can understand better what the landscape looks like there. So back on May 21st, 1970, this subdivision was halfway built. You can see the roads, the freeway, etc. And if you take a look at that yellow circle there with Interstate 5 running off to the northwest in the frame, and then that subdivision, we're going to zoom in on it. And so now you can see, again, the rilling, the gullying, obviously on a high point. It's a desirable place for a subdivision because you're going to get a nice view. It's no doubt been zoned by either the county, potentially the municipality. I'm not familiar with San Diego, so I'll leave it to the experts in the crowd that can educate me accordingly. And at any rate, it's a subdivision and it's being constructed. And so many of us have logged time in these environments. You can see the nice, very, very, very easily visible shadow of a very, very steep surface that's been artificially constructed within the bleached out portion of that subdivision. And we'll get a little bit closer that you can see it even better now. So you can see the house pads and you can see how steep those slopes are that are being made. I think that some of these slopes were being pushed in steepness. I haven't I don't know that for a fact because I don't have access to any grading records from this area yet. It's still on my list of things to do to try and track those down if they exist. But my hypothesis would be that some of these slopes were probably a little bit steeper than they needed to be. And even when I was in the field, I saw slopes that were way steeper than any conventional grading uh, codes would allow anybody to get away with. Certainly in the city of LA or in Los Angeles County, which is going to be one of the reasons why these slopes failed. So here you can look at a nice image that Carlos helped me put together. And you can see here that we've got this LiDAR image with slopes in terms of color. So, dark slopes, not so dark slopes, but you're looking at the house pads, and then you're looking at these landslides that occurred on the slopes between the house pads. So a lot of steep slopes, and that's the area where these actual failures occurred. So in a lot of these, you're looking at 35 to 40 or 40 to 45. So essentially 1-to-1 slopes that were the predominant location of these landslides in this neighborhood. And here's a picture of one. This was taken by Douglas Alden at Scripps, along with several others. You all have seen plenty of these pictures over your professional careers. You can just note here a couple of important details. The lamppost is still standing up. So again, it's evidence that you already have it, but it's further evidence that this is not a deep-seated slide. It's shallow, but there's just enough of it throughout this neighborhood that it's creating a problem. You can see the road, almost entirely, or at least 3/4 of the width of the roadway inundated, which is going to present, ingress and egress problems for the people in these neighborhoods. And you can see here again, anybody who's dug soil pits and spent time trying to figure out, where the fill natural soil contact is, it's not even possible. I mean, it may be possible that some of what I'm looking at in the bottom of this image, where the blue on the rock handle hammer is also fill, but just perhaps a little bit more camouflaged in terms of how it was compacted. The top of it is most certainly fill. You can look at the sharp color contrasts and the way that soil is just laying on top of itself in different strata at odd angles. And what you're seeing there is that you're seeing essentially just a hillside that goes back to that photo that we tracked down that has the thanks to nature and this rainfall, it's created this nice cut face for us to take a look at and to examine exactly how many meters or feet of fill are just laying on top of this slope that has bedrock underneath it, but has easily evacuated the cover soils on top. So at the very end of this talk here, just to kind of get through it and to ramp up, just to take some time, this is the actual area where the meat of this debris flow happened. And you're looking at another LiDAR slope map here. It shows a tennis club, a school that was impacted, and you can also see an assisted living home at the bottom of the hill. And you can see, even without contour lines, that you're looking at an alluvial fan that, like so much of California and elsewhere in the world, it's been built on top of. And it's been built on top of because it's favorable topography. You get nice views. It's nice to be off in the nature, etc. But that can create a problem when the area that you are that you're positioning yourself or building yourself against is potentially at risk of slope failure. So notice the incredibly steep slopes at the top of the screen, and notice the yellow circle here where the debris flow originated. So this is a historic aerials image. I know that Ron and I spent a lot of time looking at images like this, working, in the geotech field. I'm sure many of the rest of us on this call have as well. But what you can see here is that you have an image that's from 1967, and we're going to look at some headward erosion. There's a little bit, naturally headward erosion that's developing rills and gullies into this cliff escarpment. And what you're going to see here is that thanks to the annoying watermark on this image that you don't rip it off without paying them money, which is fair. Let's just say that's fair. Here it plays an actual really nifty geometric marker for us to understand exactly how bad the scope of illegal fill that was placed in this location actually is. So pay attention to this copyright sign that's right here in the middle of the red circle, and then that yellow dashed line that shows the edge of the cliff in 1967. And now let's go to 1990. The copyright symbol is there, so you can see, if I go between the two of them, look at how much of the top of that gully was filled in, but then also look at how little of all of the neighboring gullies, to the top and bottom of this area of interest in the circle were altered. Not much. But this one particular property is a gross offender in terms of, the example of how not to design your hillsides. And we're going to see exactly how much of a gross offender it is, because what I'm going to show you next is the actual drone footage that we use to make our topographic model. And what you'll see here is you will see the view of this destruction. And this is just the upstream portion of it. It doesn't even show you the road down the hill. But what's important is that something to think about here, scientifically, it's nifty, is that we have this debris that's caught in that fence near the tennis court. And we have this amount of debris that's filled up this catchment, as you can see the field of view moving up the drainage. And on top of that, we also have the source area. And we have LiDAR that gave us the topography, or that provides the topography before this event happened. So knowing the pre-existing conditions, it's, it's kind of like it's a nice, it's like an analog to a math problem where you have almost all the variables you need to make a pretty good estimate of the volume that's been evacuated. Because you know where the cliff line used to be, you know where it was, and you know how much it's been advanced due to the growth of the people that have been building this property to farm up here, or do whatever they're doing, and to create this problem. So that's a before image on the left, and you can see afterwards, on the right of the image on the left is obviously from Google Earth. You can see the tag there in the corner. That image on the right is taken from drone footage, just showing the scale of this debris flow down this canyon. This orange track on this map shows you, where I walked around over there over a couple days just to try and make sure I didn't leave any stone unturned, or in this case, any lost tennis ball unfound, because curiously, because there were so many tennis balls, anybody who spent time playing near tennis courts, or if you play tennis, there's always tennis balls all over the area. And a lot of those balls actually served as markers that made their way quite a decent way down the road. And so you could actually use the location of some of the tennis balls to show you how far the debris made it, even though the debris had been cleaned up. So it was a good way to get kind of a proxy for how far the debris flow ran out. These are some photos that show just the scale of destruction essentially that afternoon. So this is Friday evening, early Friday evening. You can see about almost a half meter of debris in the roadway, well out into the intersection of El Camino Real and then Tennis Club Drive. That's a view looking up Tennis Club Drive. Heads up for any people out there driving a Lexus RX something or other. Not even a Land Rover could probably contend with the amount of force of the water coming down that hill. So, like it says when you're out in the desert, turn around, don't drown. I mean, it's harder when you don't expect a bunch of trash to come flying down the hill at you in, urbanized northern San Diego County. But it's just another example of the impacts of an event like this, which we'll get to it shortly. But, this storm is easily causing now, I would say, more than $1 million worth of damage, easily. I haven't checked in with any of the tennis club officials lately, but the road had to be repaired. Parts of the landscaping were severely impacted. Multiple tennis courts and infrastructure were damaged. There's the cleanup costs. That's a view looking along El Camino Real. And just more photos here of the debris and that debris field from the tennis courts, and then marching up the canyon, looking at some of the nice geology of these previously well stratified alluvial deposits in this wash, compared to the blocky and chaotically organized nature of the overlying debris. So we're looking at about 1 meter of incision that's also caused from this particular debris flow as it made its way through the upper part of that canyon. You're getting nice imbrication of chunks of debris, cement on the top part there. And then you can see some nice stratified deposits below that for reference. You can also see in this image here a very well documented example of channel scour. You can see that you're getting natural sands that are just being ripped out, really left with this nice smooth surface, with sand even being left behind on top. And then you get this chaotic pile of debris over here on the right, full of roots, and advancing all the way into the background of the photograph where you can see some vegetation. Over here on the right-hand side of all these images, that blue star on that location map is just giving you a relative reference point as we march up this canyon towards the source, as we make our way up towards the headscarp. There's a little bit of residual clay layers that are underlying some of the uppermost reaches of this drainage. which is important, as we know, from a geological perspective, in the role that clay can play in terms of providing a sliding plane. But the really big takeaway here from this debris is that you're looking at, well, something I want to point out here quickly is the existing vegetation, this sort of hummocky grass, these clumps of grass that were growing in the channel that are about 1 meter high on average. We'll get to that in a bit. But despite the fact that there is clay underlying some of the source of this debris flow, when you get up into the actual drainage head, what you're looking at here on the right-hand side of the screen is, native tarry sandstone, but what you're looking at all over on the left-hand side is just essentially stacked, really poorly engineered or not engineered fill that is largely comprised of trash. And there was so much fill and trash in the top of this drainage that it actually managed to push out due to built up hydrostatic pressure against some of the rocks that were adjacent or in a sense buttressed to that trash. They were able to unleash chunks of actual bedrock. And here you can see it's almost like it's like a synthetic fault in a sense that, it is a fault. You can see the detachment plane here along the top left of the image where you have that gradient in color from tan to darker orange. And then you can see the rock that's crumbling away below it, which has been pushed out and downstream because of the force of the debris being unleashed at the top of this canyon. And when I talk about the amount of force that's being applied here, I don't have calculations or data on that. I'm just speaking somewhat colloquially on it. But the point deserves to be made that so much trash and the force of water being built up in it, finally just broke free. You can see what I mean when I keep saying so much trash. I mean, this is trash underneath this fill soil that was placed over the trash in order to build up the slope to build the agricultural area on that property. Look at that trash. We're talking bags, batteries, pieces of refrigerators, car doors. I mean, just a dump. Sinkholes were forming in the upper part of the property well before this storm came through. Some local workers said that the sinkholes were all over this field, that they could oftentimes hear water running through the field. So that's not a good thing. And then again, you've got trash on top of the sandstone, which is underneath that fertile fill soil, which is where plants were being grown for part of a kind of a random nursery type environment. So that's all important because yes, that's a lot of trash, and we've all seen trash in our time, and we take it out several days a week, right? So we know what trash looks like. But in terms of the landscape and how that impacts people, it's important because as a geologist that was local to the area, who's on retainer from the city of Encinitas, I believe his name is Jim Knowlton. I didn't speak with him directly yet, but at the time he had reported to the tennis club that it was unfortunate, but that unfortunately he was familiar with a lot of areas in sort of like northern county San Diego where just the old school grading practice was to just to do exactly what had been done in this case, which is to use trash to build out a landscape. And so by getting a study like this done to show the actual scope of destruction and what that means for the cost, and to also apply modern technological tools for topographic modeling, it's a cool story to tell, to alert to people that actions have consequences. And what that means is that we can see the tale written in the landscape. And when we look at the LiDAR that is this is 2016, obviously pre-event. It's the San Diego County LiDAR. You're looking here at the tennis club. These X's that you see, or these crosses on the screen, are actually ground control points that Alex Moreland used to get XY control on the image so that we could rectify it properly. And you'll see that. So those are the points there, and then you can see that's from the actual points on the tennis courts, which is a really precise level of control. And that control is necessary because when you're doing structure from motion modeling, typically it's a very well thought out plan where you fly a drone, you have really nice black and white or highly visible scale bar markers that you leave at different areas around the area that you're going to survey so that you can use them as a datum when you're collecting your images for your orthophotography. We didn't have that because we had the drone footage that, as you saw, was shot obliquely, but luckily it was shot with just enough of an oblique angle to capture enough of the actual relief that we wanted to model. And so combined with the NAPE imagery, it's national, agricultural imagery that's shot for all of America so that people can track land use change. And, by using that image, and then this is the NAPE image here, and then again, correlating these ground control points with what the ortho photograph was that was produced from the drone, what we ended up getting is we get a nice view of before and then after. And then you can see here that, again, before and after. And what I want to point out here is that with this bare earth DEM, there's a lot of topographic uncertainty along the Thalweg. And why is that? Well, it goes back to that photo that I showed you earlier of that plant that was about 1 meter in height. And we'll come back to that in a minute. But that's important for getting the actual vertical control to be accurate when you're looking at a drainage area, or really any topographic area where you want to strip out all of the noise from the actual true bare earth signal. And so these numbers that you see on the left here, again, just using the source of the debris flow and then looking at the amount that was entrained and then collected in the tennis court area with those fences, you're looking at, about around 2,500 cubic meters of source debris flow, 2,000 of which backed up into the tennis court, and then at least another 1,000 on the upper tennis court alone. And there's more that may have gone down the hill, and there are harder ways to calibrate that because we don't have the drone footage, so we can't actually see or detect with the structure from motion modeling. But we do know with this model of what was there before and then what was the aftermath. And then we can use the changes in topography to look at these, this heat map or this color gradient of, what is missing and what's been gained in the landscape. And so this is just another, easy to digest view of these areas: the source area, the slide outline, the depositional area in blue, and then just the volume in the tennis court alone. These cross sections here, I'll wrap it up here shortly. I know that we're at 8 o'clock right now, so thanks for hanging. But these cross sections are an important other part of the story with the topographic modeling. And what you're looking at here is that you're looking at, basically just pre-event ground surfaces that are dashed versus the post-event ground surface that's solid, or in blue in this case. And these are being constructed both, along strike and then orthogonal to the drainage, so that we can pick out some of the extra little bits of nuance to the data. And what you'll notice in cross section C to C prime, it's right across the middle of the debris field, just upstream of the tennis court. And you'll notice that, of course, the when you're looking at the pre-event Thalweg profile, it's actually much higher than where it was afterwards. And that's fine because it should be higher. There's definitely some incision that's happening in this area. And there's material that's missing because you can see it's color-coded red. But what's interesting is the way that that Thalweg is almost higher than what you would think it would be as an actual stream bottom. And as Alex and I worked through on this, one thing that explains it is that we've got our cartoon with a local Torrey pine here for reference, but all those bushes that were about 1 meter high that I mentioned are filling up and littering the bottom of that stream channel. And in so doing, what you're doing is, even after you're removing that data and stripping out vegetation, it's still uncertain if you're getting the true actual depth of the Thalweg, so that you can accurately compare before the event with after the event. And what it really means is that the current differenced volumes are potential maxima, because it could be that the Thalweg was a little bit lower, because of course it probably was, because we're looking at all this vegetation that is arguably higher than the actual true elevation of the bottom of that stream. And so it potentially is about 1 meter of offset. But a way to test that model would be to actually take a look at additional satellite data that hopefully comes through at some point, to see if we see these same aberrations in the Thalweg geometry on other slides that we can detect in the landslide data. So again, that's what 1 meter of vegetation looks like. You can see the non-scoured surface below that vegetation and how thick it is. And then also another view, how thick it is looking off to the west in this view. So just to wrap it up, that was a lot of water that fell last year. It's wild that we're supposedly in a La Nina regime right now, because it may not feel like it after the next 7 to 10 days of rainfall. So stay tuned if something similar happens in our neck of the woods down here. But triggering thresholds are important, and the reason why is because when you can use events, whether or not they're actually man-made forms of destruction or whether they're natural forms of debris flow, when you have a tight control in timing of rainfall coupled with an accurate measurement of the volume of the sediments, it's really important because if you look at this map, 2.5 of us here in California, 2.5 million, we live on alluvial fans as about 6% of the population. And that's really important because that is actually what it comes down to, is knowing your environment, knowing the built environment, knowing what sort of precautions can be taken to be prepared for natural phenomena, especially when you have really great weather system data telling you what to expect for rainfall. We don't know when to expect an earthquake, but we can have a pretty good idea of when rains are coming. And, this is just kind of a cautionary, way to understand more about, what can happen in a sort of worst case scenario. And, a lot of people don't really understand this, but when you tell people in millions of dollars how much destruction happened, that's when folks start to understand why it's so important to listen to, all of the professional geologists in our community, whether we're working in industry or, in the academic world. We're all trying to, advance the understanding that we get by taking a detailed look at the landscape following natural disasters. So hopefully this doesn't happen again anytime soon, but if it does, then maybe I'll come say hi to you all when I'm down in the field next time taking a look at it, or anybody else on our team. So, thanks a lot for your time. I know I pushed it here by a few minutes, but thanks for hanging in and for your interest. Really appreciate it. Thanks, Luke.
Yeah, thank you, Paul. That was a really great talk. So if anybody has a question, please pop it into the chat. Now, mind you, there's 100 of us, and we don't want to be here for an additional hour answering questions,
Yeah.
I don't think.
You can also email me. Yeah, anytime
yes,
too.
of
You
course,
can email
feel free
me.
to email Paul. We'll give his email out in an email if anybody would like that. But if there's a question from
Luke, I have a couple of comments and questions. Hans Jansen here. I was participating in your fantastic field trip in Temecula.
I remember. Yes, Hans. Good to see you.
Yep. I have a couple of comments from Gothenburg, Sweden, and you can look up on Wikipedia TUVE landslide. Completely catastrophic. 9 people died. About 300 houses destroyed. All landslides, they evolve from the same thing. Top loading the shoulder and undercutting the toe, and underestimating the water flows underground. Same case here in California, and it's amazing that planners never learn. What do you say about that, Paul?
Yeah, I think those are, like you're spot on with that, Hans. I mean, one of the things that you can highlight here is that so just to go through those 3 points and sort of top loading the shoulder and then, undercutting the toe and then, actually having a constraint on the subground flow of water. So what we do know from the available data, remember, if you take a look at the, let's see if I can, let me do this again here. I'm gonna, bear with me. Can you guys see the slide again?
Yep.
Yeah, thanks. Sorry, I'll just flash forward through here so we can take a look at that slope map. The rest of that slope that is adjacent to the area that failed at the top of this debris flow. Well, you can see it right here, actually. So let's just go to the LiDAR and take a look. The top of that is essentially arguably natural for the rest of that area that is adjacent to the actual area that failed. And so what that shows is that the area is relatively stable with that Torrey sandstone that's got that thin cap of actual Pleistocene gravel on top of it, which is good because if it wasn't, then we would see debris flows running out through all of these channels. And you can look at the actual width of that channel and the scale of it. So here we go. This is 100 meters, it's a few hundred meters. Typically, you wouldn't see this amount of debris entrained in a catchment of that length because there's not enough there's not enough stream power to generate that amount of debris from that amount of relief. So what we're looking at here with that nice flat slope at the top of where that yellow outline is on the area of the debris flow, that natural gully has been infilled by all of that trash. We have no constraints on when or how long that happened, but we do know that it at least was going on since 1967. The toe being cut out, it's unclear what's going on in the top parts of that drainage. It's really hard to know without having previous years of LiDAR to take a look at if there was any modification to that actual, to the actual area of the bottom of that slope or that scarp. You can tell that there's kind of an unnatural bulge on that image right there. So whether that had any sort of modification to it by humans, it's unsure. I can definitely say that more top loading was happening because more weight was being placed on it by the weight of fill that was being put on top of that landscape to create more arable, land. To me, the big issue here, well, there's two things. There's one, there's all the rain that fell, and two, to your point about subground flow, and like I said, the sinkhole development that occurred above the cliff's edge, that gives a crucial insight into the fact that this water was draining out in any way that it could, but it was most likely ponding up against impenetrable zones of just arguably, over dense packets of clay, pieces of trash that were impenetrable or that diverted water flow. And so it just got loaded and loaded and loaded. And then when you had that amount of rain, it just created this catastrophic explosion. And I would think that there are other areas in this area of Encinitas and all over northern San Diego that were developed in a way similar to this, that people would be very wise to try to educate themselves on. I mean, no landowner wants to find out that they're literally sitting on top of a pile of trash. Like, that's just not a good realization. But the utility of knowing if you are or if you're not is that at least you can be prepared, because if nothing else, you can be prepared to get ready to figure out either one, how to pay the bill, or two, how to think strategically to retain a good lawyer to argue that this was actually not your fault and it was due to the person who did it previously. But it's just kind of a mess, it's metaphorically, it's a mess on so many levels, naturally as well as interpersonally. And then there's a tennis court, there's an entire community of people living downstream. And then there's this area upstream that these people literally had no idea that this was about to unfold. So the first step to educating people with landslides is, I think it helps to have a really flashy, dynamic example of one that can just literally strike a community that probably never thought that something like this would happen. And then you can say, hey, look, a guy in 1986 worked with an agency in the state and told you that this could happen. And so that day arrived, 34 years later. So.
Right on.
Yeah.
Oh, sorry.
No, right on. I echo that. Yeah, right on.
We do have a question here. Let me hear. Okay, so from Jeffrey Anat asks, he wonders if you considered the thorn weight modeling to relate the impact of antecedent water conditions and landslide triggering.
Thorn weight? How do you spell that? I can tell you that I haven't at this moment, but I would presume that it's, how do you spell it?
THORNWAITE.
Sorry, THORNA.
NWAITE.
Thorn weight. Okay, got it. Thorn weight modeling. No, I haven't. That's great to hear, though, because there's, as I move forward, a lot of this data is going to be, put up into a publication to just document, what happened, why it happened, and then some, hypotheses on, how we can understand, especially with that disparity in the triggering thresholds, because, look at that map. This area was impacted by rain all over northern San Diego, and that's why we want to get that satellite data too. Is that we want to see if there are other areas that I wasn't able to see in the field, or that other people also didn't see, that face some similar type of catastrophic events following that rainstorm, where you would see some scars in the landscape, definitely. But we don't have that yet. And so in the meantime, it starts with cataloging what we do see. And so I'm happy to explore that model and I can contact you, by email, or happy to continue the dialogue to chat with you about that if you'd like to keep on that thread, Jeff.
Okay, we've had a new question here from Christian. Is there an understanding of how much water the owner of the parcel? Oh my goodness, sorry, just scrolled with a new comment. Sorry, forgive me. Is there an understanding of how much water the owner of the parcel? Oh my goodness gracious. Let me make the chat larger so this doesn't happen.
No, it's okay.
Forgive me. Is there an understanding of how much water the owner of the parcel where the event was triggered is used for agriculture?
No, that's a really good question. At the time that I was there, the litigation, or I would say the imminent litigation, was super hot and heavy in terms of the tennis court being just hopping mad that they were dealing with cleaning up that mess, and really in the early stages of not knowing who to blame. And I can also say that first of all, that's an excellent question, because that roots into a deeper question, which applies to the entire area, which I could tell you I don't have that knowledge right now. And it is desirable knowledge to get, because you want to have an idea of what the typical drainage flux would be for a drainage, because you have to know how that drainage is responding to your normal water years, and then even your previously abnormal water years, to look at what the signatures are and if there's data and if it's been recorded. So no, I don't have it, but it is on my list of pieces of information to collect, because you do need that, especially if you want to get into deeper, more nuanced levels of doing hydrologic modeling. So that's a great point that you've made, Christian.
Paul, one more if you don't mind.
Yeah.
Did you determine the residual clay contributed to the slide?
That is actually very uncertain to me, based on all the field evidence that I saw. The field, or the plane of failure, happened above that point, and it was the force of the failure happening above that point which is what was responsible for exploding out laterally that sandstone that you saw that was ripped off of the sidewalls of the canyon. Right. So that, to me, is one piece of actual, in the field evidence that failure plane, if you want to call it that, was being largely driven by the water that was flowing out of the field as it interacted with that massive pile of trash. I think that if more trash had been placed, or if there was more trash in the bottom of the canyon that bulged out further, then we could get into that discussion. But it's tough, because I don't know what that area looked like beforehand. And I'm just, I'm going up and I'm trying to detect in a very small amount of time, like, was this here before, or was this now, a rapidly completely destroyed area because of this debris flow? So it's a good question, and it's something that will be addressed in the write-up, in terms of leaving it on the table as a form of potential ambiguity, because we traditionally like to think of landslides in terms of that clay that can be just that traditional culprit. But one thing to keep in mind here is that the geomorphic expression of this actual disaster is more of a debris flow, obviously. And so debris flows have different, originating mechanisms, and there's a lot of complicated science that is even, I'm still climbing the ladder, to understand myself. But I know that geomorphically, being a debris flow, it's a little bit more chaotic and obviously more poorly understood than traditional landslide failure starting processes.
Right on. There's a new question, sorry, from someone named Bolson, who I think is a chain link fence distributor. What is the maximum height or thickness of debris retained by the chain link?
Okay, this is where we get into some really good, like, citizen science / ad hoc debris flow retaining side businesses. So get ready to start slinging fence before next weekend.
That's exactly.
I would say that if you look at that photograph, you saw up to almost a meter worth of debris inside that fence, with up to a third of it outside of it. And so part of what is causing it to be retained is that you have a lot of actual, larger volume debris. You've got boulders, you've got logs, you've got trash, And collectively, that's blocking a lot of sediment from actually making it out through the fence. So I would say that if you're going to build a fence, make sure that it also helps to probably put some sort of visqueen type fabric or like a plastic liner. I mean, I'm joking around here, y'all. As a professional geologist and as a working geologist for the state of California, I do not endorse this in any shape, form, or fashion. But since we're on the topic, it goes to show that a little bit is obviously better than nothing. And it's a miracle that those fences were there. Because if they weren't, then again, look at the picture. You can see it right here. It's an alluvial fan. It's just going to drill down that fan, and everything that you saw downstream of it is going to get hammered, including that nursing home, that school.
Yeah.
So fences, yeah, they help, but I guess be careful what you wish for.
Very good. Well, thank you, Paul.
Yeah.
Very much for your talk and for entertaining our questions. I really had a good time. I don't know if Lynn, if you have anything you want to say to sign off.
I have a question on the California recent reported landslide database.
Oh, yeah.
You had mentioned you would bring that back up, but I was wondering, obviously you want debris flows, bluff failures, any kind of landslides, right? You're looking for all of it.
We want it all. We want it all because, as you know, with a statistical model, you have to have a little bit of every type of event, and then you have to have more and more and more of each of them, because if you don't, then you don't have statistical robustness. So these are early days, right? Like we started this database last year, and I can talk about it forever, but I'll let you finish your comment or your question.
So what's the intent? What's the end purpose of the database, other than letting the public know where slides have happened or we've had slope failures? What is SCGS planning to do with it?
Yeah, it's pretty multi-purpose. So one example, like right now, actually, was it today? No, it was yesterday. One of our colleagues at the USGS sent us an email because he was inquiring what data the state of California had about mass landslide events due to significant rainfall events. And so this right here is a good example, right? So we have April of 2020 in Encinitas. There are probably a lot of other events like this, right? But just like all those trees that fall in the forest that nobody sees, or the rocks that fall off the outcrop that nobody knocked off with their S-wing, like if you weren't there, you can't record it. And so that's the beauty of having a database like that, is that it's a slow head of steam that builds up gradually over many years. This is a very long game sort of approach, where we want to start by taking every little piece of data, and no slide is too small. So, if you see rocks on the road, because here's the thing is, like, our staff, we're the ones that are tasked with taking a look at, like, well, do we really need to put this on the database? But right now, I would say yes. And the reason why is because anytime you have a piece of data that connects rockfall, landslide, debris flow, slump, bluff failure, and you can narrow that down to a time, then you can go back and look at the weather records. And that's when you can start to pull out these triggering thresholds, because people, even at the upper echelons of, sophisticated modeling and software, any model that we use for anything we do is only as good as the context of the data that we put into it. And so if you don't have a big appreciation for the variety of that data, then your model is not as good as it could be, And so we're just trying to do our part. And it's also a great opportunity to create a dialogue between people in California and, everybody, or at least most everybody I know, they have one of these. They're on it all the time. Some people are on it too much. And the problem is, these are a great piece of technology because they have a GPS. They have a really great phone these days, or a camera, sorry. And timestamp on the picture. So all you got to do is snap a few photos, just basically remember where you were, and then email the photo. The email address is pretty simple. It's calandslide@conservation.ca.gov. And I'll this is a project that's near and dear to my heart at the CGS. So I won't take up any more of your time right now, but what I will do is, Luke and everybody else here, I'll send you a short email with a super brief synopsis of what this is. And please feel free to just, send it out and circulate it. And like I said, I'll make you famous, because we include the basic data, and the way that it works is we have about 60 fields of data that we can put per event, like all sorts of detailed rainfall, precipitation data. But what's public facing is just, and actually I'll show you right now, I'll show you one more thing, because I have your attention right now. So let me see if I can pull this up, because I had the screen open earlier today.
Well, you know, geologists, if you ask us for pictures of slope failures, you're going to get them, because we
Yeah.
all run ourselves off the road trying to get
Right.
pictures of them.
Right.
Yeah, so you guys can all see this screen that I'm sharing now?
It is still the one from the talk,
Let's see here.
from the LiDAR image.
Let's see if I do new share screen two. Sorry, here we go. I have another screen that's hidden. So many screens, right? What about that?
That's better. Yep.
Okay, so check this out, right? So this is the map of all of California. Okay, so look at all these events that we have, and this doesn't even include the new events that we're getting ready to crank out. But what I want to draw to your attention is that, okay, so in 2018, we had the Woolsey fire around Los Angeles. If you look at here, I'll just get rid of this for a minute. This is the way it works. You know, we've got the data, you have an event, so you click on it and look at this. We've got a date, we've got a nearest place, we have the info source from Caltrans in this case. What was impacted? A paved road. The damage, well, debris went onto the PCH, boulders were observed into a channel. It's a basic observation that doesn't allow, nobody can say you're trying to drag somebody's interpretation. We've got a lat, a long, the photo credit is for Caltrans, and then this is really the power of this database, is that no other state database has this. And then look at that, that's a debris flow.
Yeah.
That is seriously a debris flow, and that's from a post-fire process. So I'll follow this up with just a little descriptive email to circulate to everybody, because it is important to me. And, you know, it starts with the actual community of geologists, because this matters. You know, right now it's in the early days, but early days become the good old days at some point, and they all roll together into, you know, a really nice comprehensive look at, you know, landslides all over the state. And so that's why we want to do it, because it affects, you know, people's homes, it affects infrastructure, and it also presents a nice opportunity to just kind of work with a lot of other state agencies, so that we can, you know, collaborate and collect this data so that we have it for the entire state. So.
That's great. Thank you.
Yeah, no, good question. You'd like perfectly led into the point that the one last point I wanted to say before we all moved on to the rest of our evenings here. So thank you, Lynn.
Well, thank you very much. That was fantastic. And we had, I think that was a record number of attendees. We had, I think, 110 people logged on. So Thank you very much. Very exciting, sexy topic. Everybody loves landslides and debris flows, almost as much as faults.
Yeah, I know.
We like them when they aren't in our own property, though.
That's right.
Absolutely.
Well, that's why, you know, for everybody in the geotechnical world, I can say this, and I know from experience, it's important who you hire as your consultant, right? Because you want people to do a good job, but you also want people to do the best job they can to, you know, be your advocate, because these are complicated problems and more than one person are usually to blame. So you've got to take a good look at the science so that you can get the best.
Well, that's a good, at the end, Bill Elliott wrote, sounds like this is a full-time employment for the lawyers.
Yeah,
it's true.
It is. Well, yeah, thank you all so much for your time and for the opportunity to share this with you. It's really, it was a great time speaking with you. And again, you know, for everybody that is, you know, hung on to the end of the talk, and even to your nice comment about the landslide database, Lynn, it was a great way to wrap it up. So
We're
you guys
very happy to have you, Paul. Very happy to have
That
you.
was great.
Yeah,
Paul, you hung on till the very bitter end.
okay.
Yeah, thank you, Paul.
Yeah, well, thanks everybody. And you know
Thanks,
what, like,
Diane.
feel free to
Thanks,
drop
Lynn
me
and Luke.
drop me a line anytime if you have any other questions about landslides or anything else that, you know, the CGS does, or, you know, data products, etc. Happy to, we are here to serve and to help you. So